Transistor is a three-terminal device, and the three terminals are base, emitter, and collector. Because of this, we have three transistor configurations. The first configuration is common base configuration. The second configuration is common emitter configuration. The third and last configuration is common collector configuration. Out of these three, common emitter configuration is mostly used because of various advantages. In this lecture, I will explain common base configuration. In common base configuration, base is common to input and output circuit. This is input circuit. This side is input side and this side is output side. If you see the direction of emitter current in the transistor symbol, you will find this transistor is an PN transistor, in which this is emitter, this is collector, and this is base. So base is common to the input circuit and the output circuit, and it is grounded in common base configuration. I am calling this side input side and this side output side because weak signal is introduced on this side, and we have amplified signal on this side, and this will happen only when the transistor operates in active mode. So there is amplification of weak signal in active mode. There are two junctions in transistor, junction J1 and junction J2. In active mode of operation, junction J1 is forward biased and junction J2 is reverse biased. Junction J1 is the junction of diode EB. Junction J1 is the junction of diode EB. Junction J2 is the junction of diode BC. We can consider transistor as two diodes connected back to back. So diode EB is forward biased and diode BC is reverse biased in active mode. I will forward bias EB. Let's say this resistance is RE. Emitter is N-type material and base is P-type material. So emitter is connected to the negative terminal and base is connected to the positive terminal, and I will call this forward biasing potential VEE. Now I will reverse bias the diode BC. This resistance is RC. Collector is N-type material and base is P-type material. So to reverse bias BC, collector is connected to the positive terminal and base is connected to the negative terminal. I will call this reverse biasing potential VCC. If I compare diode and transistor, diode is a single port device, and transistor is a two-port device. In case of diode, we have simple VI characteristics. But in case of two-port devices like transistor, we have input and output characteristics. In case of input characteristics, we have plot between the input current. The input current in this circuit is IE, the emitter current, and the input voltage is VBE. And in case of output characteristics, we have plot between output current is IC and output voltage is VCB. So the next thing is to find out direction of currents IE, IB and IC, and what is this voltage VBE and this voltage VCB. From the symbol of transistor, you can see the direction of emitter current IE is like this, and direction of base current IB is like this, and direction of collector current IC is like this. If you don't know how we have obtained these directions, then please watch the previous lecture. I have explained how we have these directions in the transistor circuit. VBE is this potential. If you neglect RE like I did in the previous presentation for the sake of simplicity, then you will have VBE equal to VEE. This is what we have. In the same way, VCB is the potential difference across the base and collector, and VCB is equal to VCC if we neglect RC. Now there is one very important thing that I want to explain. You cannot write VBE as VEB. If you follow the proper nomenclature, you cannot write VBE as VEB, because B is at higher potential and E is at lower potential. So B will come first, then will come E. In the same way, if you see the collector, it is at higher potential and base is at lower potential. So in representation, C will come first and later will come B. So this is important thing. If you follow the proper nomenclature, you have this representations for input voltage and output voltage. I'm not going to explain the input and output characteristics in this lecture. We will continue with them in the next lecture. In this lecture, I will use KCL to obtain the relation between the emitter current, the base current, and the collector current. We already know from Kirchhoff's current law, the sum of entering current is equal to the sum of leaving current. In this circuit, you can clearly see IE is the leaving current and it is the only leaving current, so it is equal to IB plus IC, because they are entering currents, IB plus IC. So this is the first equation that we have in this lecture, and it is very important. There is one more thing that you must keep in your mind. This equation is true for active mode of operation only. The next thing is the collector current. The collector current IC is equal to alpha times IE plus ICO. This is the reverse saturation current. I will rename the reverse saturation current for the common base configuration. I will add B in the representation, or IC is equal to alpha times IE plus ICBO, where this B stands for the common base configuration. The next thing is the comparison between the emitter current IE and the reverse saturation current ICBO. This O stands for open circuit, because we measure this current when the emitter terminal is open. When we compare IE and ICBO, the emitter current is greater than the reverse saturation current, because reverse saturation current is due to the minority charge carriers and they are very small in number. So we can neglect ICBO, and IC, the collector current, is simply equal to alpha times IE. So we can say that alpha is equal to IC divided by IE. This is very important relation. Alpha is equal to IC by IE. Now what is alpha? Alpha is common base current gain. Alpha is common base current gain, and you already know gain is equal to the output by input. IC is output current and IE is input current. So alpha is the common base current gain, and it is also called as amplification factor. Amplification factor. So these are the two names for alpha, and alpha is between 0.95 to 0.98. This implies 95% to 98% emitter current is the collector current, and this also implies there is 5% recombination in base, and in this case there is 2% recombination in base, and base current IB is equal to 1 minus alpha times IE. So these are the important relations that you must note down, and I think this is all for this lecture. If you have any doubt, you may ask in the comment section. In the next lecture, I will explain how to obtain the input characteristics in case of common base transistor.